Hello, everyone. Thank you all for being here today, and I'm pleased to be with 𝗃𝗵𝗃𝗀𝗃
Hello, everyone.
to present you our webinar dedicated to the assessment of natural ventilation, especially in urban area and with numerical tools. And there will be four major parts. The first one will be the dedicated pressure field on buildings and potential of natural air ventilation. Secondly, we will focus on the assessment of air exchange rate through openings. On the third part, we will be focusing on how to use the pressure field computation to the optimization of your opening positions. On the last part, we will present you our software dedicated for this assessment of natural ventilation called 𝗀𝗏𝗏, which is a tool using the CFD core calculation. And at the end of this webinar, we will have a 15 minutes session dedicated to the questions you may have. And also, if you don't answer all your questions, don't worry, there will be a replay of this webinar and a list of all our answers to your questions. And on the next slide, I will present myself. I'm just the business manager of the urban product line at Metodyne, and I'm working with 𝗃𝗵𝗃𝗀𝗃, which is here today to present you the expertise around the climatology in urban area.
Yeah, thanks, Guillaume, for this introduction. So, myself, I'm working in Metodyne since 13 years now as a urban climatology expert, and I'm also technical project leader for 𝗀𝗏𝗏𝗃. So, I think you're quite excited about this. We are quite excited to present you this webinar. Let you, Guillaume, to carry on.
Thanks, Guillaume. So first of all, just to introduce Metodyne for some people who doesn't know us yet. Metodyne is a society, a company committed to being at the forefront of the technology innovation for our clients. And we have a dedicated team of 15 employees around the world, specialized in the wind engineering, climatology, and meteorology side. And first of all, we developed our own computational fluid dynamics tool, especially for the simulation of the wind and solar radiation. And today, we provide wind engineering expertise for our clients and for their project. And also, 𝗀𝗏𝗏𝗃 today is a software, but it can be used for our services consultancy part, dedicated for all the projects in urban area. And I leave the floor to Guillaume, who will dig into the natural ventilation subject on the next slide.
Okay, thanks again, Guillaume. So you can write me any question in the chat panel and we will answer you at the end of this webinar. So let's start by the basics. What is the wind? It's an air motion that induces force on the walls. You have here a sketch, and we have the wind that is blowing from the right to the left. And as we get high pressure on the upwind condition, we have also low pressure on the downward side. So what's get inside the wind from high pressure to low pressure, and we will have, of course, wind flow inside the rooms. So when we know that, how to design the master plan. So the first thing to know is that, of course, the pressure on the wall depends strongly on the building shape. It will be completely different, the pressure distribution on the square shape and on the complex shape. Another important thing to remember that wind in urban area are really different from those nearby the station. because your project is usually the one you can get from the airport or outside of your project. That's what I'm going to explain you now on the next slide. So about the complexity of the wind pattern in urban area, have here an example of the reference station of the metadata. So you can see that the wind in this wind rows, its prevailing wind is coming from the east, and mass data at 10 meters above the ground. Then now we will have a look on the wind rows inside the urban area. On this example, we're going to extract at several places the wind rows. So if we have a look on the bottom one, we still have the prevailing wind coming from the east, but it's less. There are less wind than at the west reference station, because you have roughness which is a little bit higher than before that at reference station, so you have less wind. And now if we get inside, if we have a look on the top right wind rows, you see that the wind flow has completely changed. The wind pattern is now coming from the south. Yes, the wind flow has been deviated because you have this kind of effect, corner effect. So everything is changed. And if we have a look a little bit in the upper part right, it looks like you still have also the north direction, but it's a little bit less important. So here the idea that the wind does not look like what it looks like outside of the project at the reference station, because in the city it will be completely deviated, and also the mean speed will be usually less than outside the project. Okay, since let's have a look on the next slide. I'm going to show you also why does that happen. So we will have an idea of the most important effect. So let's start with the corner effect. It's happened when you have a tall building. The the heat will hit the buildings and go downward, and you have the wind have no choice than exit on the corner, and here you will have a shear layer that causes turbulence, and you will have a strong acceleration. You can see with on the right you have top right, it is the velocity field, and you have acceleration with the red spots. And it means when you have strong acceleration, you have low pressure. It's on the bottom image you have with the blue at the corner, you have a low pressure. So this is the first effect called the corner effect. Let's have a look on the second effect called the 𝗁𝗁𝗏 effect on the next slide. It happens when you have two buildings in a row. It will hit the second buildings, and it cannot exit, so it's going to swirl and going out also with a corner effect. So you have actually two vertices. If you have a look on the CFD picture on the top right, you have a small vertices and a big one. So this will cause a lot of discomfort, but also you will have high pressure in the front. You have the pressure map at the bottom. So high pressure in the first buildings, upwind condition, and low pressure on the second building, downward condition. And in the middle, you have intermediate pressure. So this will affect a lot the pressure distribution. And the last, the last effect, probably the most famous one on the next slide, it's called the Venturi effect. It happens when you have two buildings or a row of buildings. And you will have this acceleration in between buildings. It's you have the color map here on the top right of the velocity field. When it's red, it's your high acceleration. And you have also the field, which is a mistake. It should be, sorry about that, the pressure field. Sorry, the pressure field. So you have a low pressure, and you should have a blue color. So these are the three main effects that happens in the pattern in the urban area. So I will show you on the next slide what influence the master plan. Is of course all that effects. It will be a mixture of all that effect, conductor, Venturi effect, and Wise effect. So imagine that for one direction you will have one conductor effect, and for another direction you will have a Venturi effect. It's what we called the synoptic wind direction. So the wind that exists above your project. So you need to take into account several wind directions to be sure that you capture all that effects. So in order to do that, you have several solutions. You have, of course, the full-scale experiments. It means that you need to set up meshed data in your project and run for several months. So it's quite expensive to run this kind of experiments. So usually you could go with a wind tunnel with scaled down model experiments, which is also quite expensive. So nowadays, or I would say more likely since decades, you have a numerical approach. One is now very popular and reliable and fast. It's CFD, but you have other approach nowadays with artificial intelligence. Or also you have another kind of numerical solution with constant mass flow, less accurate. But now I will present you later the CFD. So next move on the how can you assess the natural ventilation. I will provide you some let's say easy, simple formula to assess that. So the idea is that you have two openings, and you will compute the flow rate across the buildings or across the room. So what you will need is what we call the pressure coefficient. So this is connected to is linked to the high pressure or low pressure. It's a number. It's usually between -2 to +2, something like that. And it's when you got your pressure, you can derive quickly your pressure coefficient. So the first thing is that, and what you need also is the size or the surface of your openings with the A, and 1 and 2 is referred to each openings. And you need another, let's say, a number is this coefficient C. It's for the discharge coefficient. It's how much pressure you're going to lose inside your opening. So it's a reference that the provider of the window can give you. So once you have that, you can, and of course you need the wind speed. Of course, it's mandatory. So you can actually try to simplify this formula by saying you compute an equivalent of a surface of average surface of the two openings, and it's proportional to a reference wind speed and the root mean square of this difference of pressure, coefficient of pressure. So how you will ask me, how can I get my pressure coefficient? Well, you have several ways. You can extract them from Eurocode. You have those for simple shape. You have also, you can get them from literature from the lidament. So it's also quite simple shape. And you could also use parametric models. So you can find that in the literature. Okay, so let's move on the next slide. I would like to show you how you can estimate the potential potential of natural ventilation. So this is kind of also a simple formula. It is available for tropical warm climates, so it has to be adjusted to your climate. So it's coming from Morrow and Gandemer. The same idea is that you compute the delta CP between when you have the highest CP and the lowest CP. And then according to different range, you have the potential of natural ventilation. So it is between 0.17 and something like 0.53. So you have extracted in different colors, and I've made an example here on the right. Each you have this example with a pressure coefficient map, and for you have an arrow that's going through the units, through the rooms, colored. So what you could see, for example, the upper left buildings, single detached. So you have a blue arrow. It makes sense because you have something like it's red in the upwind condition is something like 0.7, and downward condition it's maybe something like minus 0.8. So the delta CP is something like about 1.5. So you have very good potential of natural ventilation. And whenever you have some, let's say, blockage effects, like the building, separate building just upper, when you have 3 arrows from red to green. On the left part, you have some blockage effects, so you have less wind in the upwind condition. So that's why it makes sense that the potential is very low. Whenever it's less disturbed on the right part with the green arrow, you have more potential natural ventilation. So this kind of formula can help you to quickly assess with just a map of pressure coefficient. So this is adapted to this kind of climate and need to be adjusted, as I said. Okay, so let's move to, I would like to talk to you I went through a simple case with one room, I would say. So if you have multiple volume, so how you do that? Well, you need to compute first the internal pressure. Then you can compute the flow rate, the mass flow rate over the whole volume. Once you equilibrate this mass flow, you equilibrate the pressure for each room. So how we do that? We will use this formula, which seems maybe a little bit tricky, but it's actually quite simple. You need to process as an iterative process, and you need to adapt each time the derivative of the pressure. So here we have, I'll show you here an example of the windrow. That first you need to compute the wind speed. You need to compute the pressure coefficient, and then you can assess directly inside the internal pressure and get this flow rate for each door. So this is the microscopic approach. Let's move on to the next slide with the mixed CFD microscopic approach. So the idea is that you compute the pressure coefficient. So how we do that? We first need to collect the climatologic data. It can be either by frequency table or by time series. Then you compute the pressure coefficient, and you can get so distribution of pressure coefficient for this direction and the reference mean speed. These two, it's linked to the simple formula I showed you before. You need the reference wind speed, pressure coefficient, or distribution of pressure coefficient, and some characteristic of the openings. So once you run this CFD, you can easily get statistic of air change rate, and also you can get extra more data with time series of mass flow rates. Okay, so let's talk now a little bit of, on the next slide, of 𝘂𝗏𝗏. So how we do that? It's quite straightforward. You need a model of your buildings, of the surrounding. So it can be buildings around with trees, with topography. You need, of course, it will affect the flow patterns around your project. So more details it is, the better the best is. So once you set up your case, you run your simulation. So there is this internal process where you're meshing define boundary condition and run CFD. And then you will get this pressure coefficient for several directions. Once we are finished with the CFD, you import weather data. So you have your reference wind speed. You define your openings, where are they, what is the size, and you can define also what's going on inside with internal porosity. And then you can compute mass flow rates and air change rates. You can also export CP for each openings and for each wind direction, so you can link with thermal software. Okay, on the next slide, I would like to sum up a little bit about the inputs file and the outputs. So basically, for the input, you will need so all the CAD, topography, and trees. They are all defined in this simple format called STL format. So all the software can export this kind of formats. And for the weather data, it can be so frequency table and time series. I will show you a little in the next slide what is it exactly. So you run the simulation, and then you can export. So it can be else you can visualize. So you can export JPEG or BMP, wind rows or air change rates. And you can also export time series of air change rates and pressure coefficient also for each openings. So these are the outputs. And a little bit now, let's talk about the weather data. On the next slide, so we need for the weather data, there are several sources. If we could, yes, so you could ask directly to your national weather data. So in France, we have Météo France. In UK, you have Met Office, NIWA for New Zealand. Many. And you can ask for them. You can also go for free data on NOAA. So there is this agreement between countries to provide and to collect on NOAA free data. So it's free, but the drawback is that it's not checked. So you could have issue on the data, such as a probe which is not working, such as you could have a building very close and it's completely disturbed. So you have to be careful of those free data. You could also get from 𝘃𝗲𝗃𝗃𝗃𝗃 EPW. So you have a lot of them. If you look for EPW on Google Earth, probably the best way is with Ladybug website. You have a lot of EPW. You have also another way from a software called 𝘃𝗀𝗯. It's not very expensive, and you can extract with the data. There is this kind of interpolation in between two airports. It's sometimes, well, it's useful, but you have to be careful whenever you have topography, which is not flat. And the last way will be with mesoscale. So it's large HL scale, that's run with software such as 𝘃𝗀𝗃, the most famous one, and you can have very good resolution. And there are many websites that can provide you this kind of simulation. So once you get your data, you need to little bit to post-process them. There are files on the next slide. So it can be time series or statistical information. Nowadays, statistical is less and less common because we have much more free data, I would say. Yeah, in the past, it was very costly time series. Nowadays, not that. We have this process in France with open data. So it cost a fortune in the past to get weather data from Meteo France. Nowadays, it's free. So it's in a good way. So time series better in any case. So you need to convert it, but it's quite straightforward. You need two or three column, wind speed, wind direction, and time and date. Very straightforward. Okay, on the next slide, I would like to talk you to last but important subject is do not forget to correct your weather data. It is not a topic today, but it's an important step. And this is a webinar I would like to talk to you during the fall in September, October. So because of course the wind at the weather station in open land will be completely different with the wind in your project. So you need to adjust the land occupation, and also it may be affected by the local topography. So all this matters, and so important points. Okay, let's move to think now. I'm going to move to the example. So I would like to, sorry, I forgot this part. So some quick words about some norms and recommendations I found. We have in France on our overseas, we have some recommendation, which is mean speed should be around 1 meter per second. So you can extract energy from the house, and you can drop temperature drop of 4 or 5 degrees, and also you need some, if possible, some air change rates quite high. So it means that you cannot, also you don't want to be above 2.5 meter per second, because it's quite well annoying. For you could have a sheet of paper flying in your room, so you don't want too much wind. In Oceania, it's basically the same order of magnitude, so something like around 1 meter per second. And there is another way to look at. They look at the weekly max min, but it's the same order of magnitude. Okay, now on the next slide, I would like to carry on with some examples. So I've gathered 3 examples, 2 in overseas of France and another one in France. So in La Réunion, there were these existing buildings, and the owner wanted to optimize the natural ventilation. So you have the plan, 2D plan on the bottom right. There are these existing windows, and he wanted to open inside the rooms to improve natural ventilation. So the first thing is compute CP. Always compute natural ventilation, and then define the characteristic of the openings and get the ETH. So here also we in addition to add new windows, we could also optimize the characteristic of the windows, of the existing windows. So if because we wanted to add Stokes effect due to buoyancy effect here, because sorry, I forgot to mention that in 𝘂𝗏𝗏 we do not take into account thermal effects. We take to account only aerodynamic pressure. So in order to compute that, we export the CP outside of 𝘂𝗏𝗏, and we use design builder or 𝗃𝗲𝗶𝗹𝗁 as an input. So we could compute Stokes effects in addition to 𝘂𝐻 due to aerodynamic pressure. So this is the first example. Now let's go to another example, and another overseas in New Caledonia. So the idea in New Caledonia on the next slide is that we wanted to assess natural ventilation over this school. It was quite interesting potential, so we wanted to assess that. So same methodology. We first need to compute the pressure coefficient around the buildings, compute the reference wind speed, and then according to generate those formula, the ACH, we need to provide characteristic of the openings. So by characteristic, we need to define the location, the size of the openings, and the discharge coefficient. So it was done, and we can easily assess that. Okay, next and the last one is a case we have done in France. So this one wind effect was not enough, so we need to take into account the Stokes effect, because we deal here with the tall buildings, so much more important Stokes effect than natural ventilation due to aerodynamic effect. So the idea is same: compute pressure coefficient, get the mean speed, derive the characteristic of the openings. So we could get easily the pressure coefficient due to the wind, and with a simpler formula from the literature, we can derive the Stokes effect due to the difference of temperature between the interior and exterior, and the height of the buildings. So what we could see that it's actually quite important the Stokes effect whenever you have quite a high important volume. Okay, so let's finish by the next slide. A little bit about the performance. So the CFD usually runs in a few minutes whenever you have this kind of simple shape with 20 ΔHBD. It takes a few minutes. Run on a simple laptop. When you are dealing with a suburban area with a lot of buildings, it can be up to 30 minutes. When you are running with a even larger suburban area, it can be a few hours. And when you want to run in complex case with topography, vegetation, skyscraper, it can be something like around a day for one direction. So it can, for those who are not familiar with CFD, it could seems big, but it's not that big compared to our competitor. And but it's big compared to thermal study. And you can actually go faster whenever you have more CPU. Okay, so I think I've done with the presentation. Hope you enjoy it. And now it's time for question. I will be very happy.
Thank you, Guillaume. And I think
Welcome.
we got already some questions available. And of course, you will have access to this the replay of this webinar by email and downloading part. And also, if we don't have answered all, didn't have all the answer today for your questions, you will have a summarizing part by email. And the first part question is that, is it a part of the same software, 𝘂𝘂𝗶 or another software? Of course, the natural ventilation module is a part of 𝘂𝘂𝗶 software, and it can be added to complementary modules as small turbines or pedestrian comfort. So you can choose what will be the modules that will suit you the most. And of course, it can be added to complete solution.
Okay. Another question: Is it this webinar? Is it recorded? And can you share it? Yes, we will share it later. We send all the materials. Another question: How is it generated ACH? So as I said, once we solve the equation with the derivative of the pressure, we get the internal pressure and we get the flow rates for each openings. For each time step, we're going to compute the flow rates, time step of your wind data, because it's time series data. And so we can extract temporal mass flow, and so because you enter the volume of the room, you can get temporal ACH. Okay, so there is a question about the modeling of the window of the openings. Yes, so it is not CFD inside. It is what we call the neural network. So basically, it's like electrical scheme. We add some, I'm not sure if it's English, resistance for each openings. It's like a pressure loss, and we solve this scheme. There is no CFD. There is no 2D model or 3D model. It's 1D. Because we know the surface of the openings and we know the discharge coefficient, we can estimate the pressure loss for each openings. Okay, yeah, I know there are a lot of questions about adaptation of the weather, file according to the environment. So I know that a lot of people also from Israel are, and all over the world are very interested, and of course we will provide you with it since it's a tricky question. Is the 3.3 provide pressure on the facade? Yes. If you have the natural ventilation module. So if you have wind comfort, it does not provide this information. Another question is this, but I'm not sure to understand the difference between the wind speed frequency and the 𝗶𝗃. I'm not sure what is the 𝗶𝗃. So I'll let you provide you more information about that acronym. So quite a lot of questions today. Okay, there is a question. Do you want to answer that, Guillaume? This question about wind simulation for all kind of publics?
Yeah, thank you, Guillaume. So today, when you are going to do a wind simulation, the urban wind software is dedicated to be understood by all actors in urban planning world. So the idea is to not be an expert on the CFD part. You don't have to know all the equations to understand what we are doing with the urban wind, but it will be dedicated for the analysis of the wind impact on natural ventilation as pedestrian comfort, and the idea is to have a visible result to be sure that the design, the planning design is in a good way, in a good shape, compared to the final objective on the pedestrian comfort and natural ventilation of your building. So in today, all urban planners are architects, urbanism employees can use 𝗶𝗏 and can have an easy way to understand the wind impact in urban area. And I think you got an answer for the 𝗶𝗃 acronym.
Yeah, okay. So pressure coefficient, okay, yeah, sorry. So pressure coefficient by definition is the difference of the pressure between two phase and the dynamical reference pressure. And the pressure is related, if we have a look on the simple formula Bernoulli, with the velocity of the point at the point you are looking at. So when you have high velocity, it's low pressure, and well, that's it.
Okay, so I think we answer many questions at this time, and we got more and more coming. So I think we will do a summarizing part regarding the questions we have today and we didn't answer yet. And also, if you got question after this webinar, you can join us by emailing Guillaume or I by email, and also you will have an access to this webinar by replay, and we will communicate more and more in the future about new webinars and also new tools or advice to help you to increase your knowledge on your wind. So thank you for your time and for joining us today. And don't forget to share with us some comments afterwards.
Thanks a lot, everyone, for assisting this webinar, and hope you like it. And well, enjoy the summer, and let's meet again at the fall to present new webinars. Have a good day.
Thank you. and bye.
Bye-bye.